Hello everyone, this is me, Muhammad Bilal Khan from Kaohsiung Medical University, Taiwan. Today I will present my work title is Multifunctional DES-based sulphur-doped graphene quantum dots as antibacterial, antioxidant, and fluorescent nanosensors for ultrasensitive and selective detection of chromium-VI. I will start from introduction. Serious health problems are caused by toxic heavy metals like chromium-VI and other toxic heavy metals, and also the growing antibiotic resistance worldwide, which pose a lot of health risk for all the humankinds. Hexavalent chromium is a highly toxic heavy metal that poses serious environmental and public health risks, which currently initiating the development of sensitive and reliable detection methods for heavy metals and also for other analytes. And antibiotic resistance and multi-drug resistant bacteria are also a major global threat that make infections harder to treat and highlight the urgent need for new and effective antimicrobial agents. What are our objectives? Novel DS-based sulfur-doped graphene quantum dots synthesis, characterization, and explore their application as fluorescent nanosensors and also as antimicrobials and antioxidants. So what are the methods we are applying and methodology? First of all, sulfur-doped graphene quantum dot synthesis. So for this, we need to synthesize deep eutectic solvent synthesis and then sulfur-doped graphene quantum dot synthesis. Then characterization of the synthesized sulfur-doped graphene quantum dots through transmission electron microscope, EDS, DLS, SAED, FTIR, XPS, UV-Vis, and fluorescence spectroscopy. All of the analytical techniques were used for this compositional and structural confirmation of sulfur-doped graphene quantum dots. And then we checked chromium-VI detection as their application and also selectivity with competing ions, mechanism studies, and also their antibacterial and antioxidant studies. And then we also check our sensors ability in real samples, taking the sample from Lotus Pond here at Kaohsiung City in Taiwan, and also used our lab tape water for analysis. Now we move forward to the results section. So first of all, image A is showing the representative diagram of the sulfur-doped graphene quantum dot synthesis. B and C are showing the optical properties, and B is showing the visible spectra. And also the high and C is the highest emission spectra, which was at a wavelength of 440 nanometer. And then through TEM and HRTM, we check their structural morphology. And from DLS, we see that the average size of graphene quantum dots was less than 10 nanometer and was around 3 to 5 nanometer. And from SAED patterns of the specific area, it shows the polycrystallinity of our graphene quantum dots. And then from the compositional analysis, we checked the XPS spectroscopy and also HRXPS spectroscopy. So from HRXPS, we can see S2S, the sulfur compositions, carbon and oxygen bonds on different binding energies. After that, we did for the application of the chromium-VI detection. So in the A inset showing the visual representation of the fluorescence quenching of the chromium-VI through sulfur-doped graphene quantum dots. And we used long and wide range from 1 micromolar to 350 micromolar. And in B, it's showing the limit of detection through the linear regression analysis, and it showed that 116 nanomolar was the limit of detection. And then C is showing selectivity studies which we did with the competing different anions and different cations, including other heavy metals and anions. And it clearly showing the fluorescent quenching ability of the chromium-VI versus other competing ion. Then we checked for the mechanism of this quenching. So for there are different types of quenching mechanism. So for this we take the emission and excitation spectros of sulfur-doped graphene quantum dots, and then we checked with the absorbance of the chromium-6. So we can clearly see it is overlapping with the excitation of the sulfur-doped graphene quantum dots. So when the absorbance is overlapped with the excitation of the fluorophore, then the mechanism will be inner filter effect. And for this, we also did the TRPL assay, time resolved decay, before and after adding of chromium-6. So we did both before and after, and we did not find any change before and after. And then we check for the ground state complex formation. We take the absorbance spectros of chromium-6 separate and sulfur-doped graphene quantum dots separate and also together. So in the together, we already see the complex formation, and from this we can confirm its static quenching mechanism. So our quenching mechanism was dominantly by IFE, inner filter effect, and secondary by static quenching mechanism. Then we explored their antioxidant and antibacterial activities. So we did DPP scavenging assay to find their antioxidant quality. So we can clearly see we use 10 micromolar, 20, 50, 100, 150, and 200. So we can see at 200 micromolar, the efficiency was more than 90% of the S-doped graphene quantum dots. So it was very showing, and it was also surpassing the control ascorbic acid. So it was very good antioxidant activity. And for the IC50 values, we can clearly see 28. It was higher than sulfur-doped graphene quantum dots. For IC50 for ascorbic acid was 28, and for sulfur-doped graphene quantum dots, it was only 25.877. So it shows clear antioxidant activity. And then we check the primary antibacterial activities through disk diffusion assay, and we took multi-drug resistant strains of gram-positive Staphylococcus aureus and gram-negative E. coli, and we checked through 1, 2, 5, 10, and 20 micromolar per ml. So it clearly shows the zone of inhibition, which was around 20 to 25 milliliter inhibition millimeters, and also in more than like 25 millimeters. So and then we checked the MIC, minimum inhibitory concentration, for this. So for it shows the concentration of the E. coli was the bacterial growth of the E. coli was more suppressed by the sulfur-doped graphene quantum dots compared to the gram-positive multi-drug resistant Staphylococcus aureus. And inhibition efficiency was around 95 or 90% for the E. coli at 20 microgram per ml, and also at 80% for Staphylococcus aureus. So it was good antibacterial activities. And then we checked the live and dead cells for the before treating with the graphene quantum dots, and also after treating with the sulfur-doped graphene quantum dots. So we can clearly see, and we stained our cells with the propydium iodide and acridine orange for live and dead. So the red cells showing the dead cells and the green showing the live cells. So at 20 microgram per ml, we can clearly see the red cells which are dead are more prominent and dominant than the live cells. So from this we can also confirm the activity of the sulfur-doped graphene quantum dots for both E. coli and Staphylococcus aureus. And now we move forward to the conclusion. The sulfur-doped graphene quantum dots serve as a sensitive and selective luminance sensor for chromium-6 detection in the wide range of 1 to 350 micromolar with a detection limit of 116 nanomolar. And it also shows high stability across time, temperature, and pH. And also they also showed strong antibacterial activity with MIC of 5 micromolar per ml and high antioxidant efficiency 91%, and by sulfur-doped graphene quantum dots, and ascorbic acid was lower, which was 85%. And these results suggest that DES-based sulfur-doped graphene quantum dots for future chromium-6 sensor development. And also, our approach can be further expanded by utilizing DES to develop diverse graphene quantum dots based nanomaterial, graphene based nanomaterials for detecting various analytes in medical, biological, and pharmaceutical and environmental sensing applications. Thank you very much for your listening. And if you have any question, please let me know. Thank you very much.